Let's discuss equations of lines and planes, our next topic in this exciting calculus course. Now, you know about lines in two-dimensional space, in R2. So we're talking about lines in R2, and how do we describe a line in R2 with an equation? Well, let's suppose we had some line living here in R2. We needed to know two things to describe this line with an equation. We needed to know one point on the line. So say we had some point here, and we sometimes refer to that as x1, y1, and we needed to know the slope. And so if we had that the slope of this particular line was some value which we call m, then I know how to get from one point to another. I just go, well, so far to the right and so far up, or so far up and so far to the right, and I can get to any other point here on my line, namely any point x, y. In other words, this ratio here of the change in y values, so y minus y1, over the change in the x values, x minus x1, where y or x comma y is any other point on my line, given this point I know x1, y1, is going to be equal to the slope. And then of course we can do a little bit of algebra here to put this into what we call point slope form, and there it is, y minus y1 equals m times x minus x1. But we needed to know two things. We needed to know the point, or a point on the line, any point will do, and we needed to know the slope of that line. Now let's talk about the analogous concept. Well, somewhat analogous. Really, planes are more analogous to lines. Planes in R3 are more analogous to lines in R2. But let's talk about lines in R3. So here we're going to think about the visual of our three-dimensional space, our x, y, and z coordinate axes. And we're going to have some line maybe coming up like so, and going like this. So we still need to know a couple of things now. One of those things we need to know is still going to be a point on that line. Now this has an ordered triple. I'm going to call it x naught, y naught, z naught. Okay. Now I can't really talk about the slope here the same way I can talk about that in R2. The slope I could talk about in R2 is just the change in y or the change in x. Well, I've got three variables to worry about here, x, y, and z. If I go from one point to another on my line, my x value is changing, my y value is changing, and my z value is changing. And so we're going to use vectors to describe that change. So picking some point x naught, y naught, z naught, I'm going to take a vector that lies on that line, so it's going to be in the same direction as that line. I'm going to call that the direction vector of the line, and then that will point me to get to another point on my line. So I can call this direction vector v, and then just by taking scalar multiples of this direction vector, for example, I could extend it out here, I can get to any other point on my line x, y, z. So it's all going to be made hopefully pretty clear here. We need two things for the equation of a line in R3. One of those things is a point on the line, just like we needed that for lines in R2. The second thing, however, is instead of slope, we have the idea of a direction vector, a vector that lies on our line, a vector that is in the same direction as our line. Usually we refer to that as v. Okay, so here's what we have then. I see I have my point on my line, x naught, y naught, z naught, be a point on the line, and suppose that line again has direction vector v. Then, if we have any other point on our line, x, y, z, or we want to be able to describe all the points that are on that line in terms of x, y, and z, we're going to have the following. I'm going to form the vector from x naught, y naught, z naught to x, y, z. So that looks like this: x minus x naught, y minus y naught, z minus z naught. Well, that's going to be equal to some scalar multiple of our direction vector. No matter where I pick my x, y, z on my line, I can multiply the direction vector v by some positive number or some negative number if it's going in the opposite direction to get that vector from x naught, y naught, z naught to x, y, z. That changes the length of it. So that's going to equal to some t times, well, t times v let me go ahead and write this as t times a comma b comma c. So let's let our direction vector v be the vector with components a, b, c, just in general terms. Okay. So what do we have here? This, if I include that a, b, c there, this is what's called the vector equation of our line. And if I go ahead and equate these two vectors and pull out the components, then we're going to have what we call our parametric equations of the line. That is to say, I have that x minus x naught is going to equal t times a. Y minus y naught is equal to t times b. And z minus z naught is equal to t times c. So I can solve each of these for x, y, and z respectively, and that's going to give me my parametric equations. In other words, x is equal to x naught plus t times a. T is just some scalar, remember. It's just some multiple for this vector here. That'll extend it and send it in the right direction. So we get the vector from x naught, y naught, z naught to x, y, z. And so y then is y naught plus tb, and z is z naught plus tc. So I've described this line in R3 with a series of equations, one for x, y, and z each. These again are referred to as the parametric equations of the line. T here is what we call the parameter. Now we actually have one more form that we can put these equations in, and that is if we solve for t, in each of these I'm going to have, let's see, solve this one, x minus x naught over a. So all these would be equal to t, right? If I solve the second one for t, subtract a y naught, divide by b, so that's also equal to t, y minus y naught over b. And the third one, subtract a z naught, divide by c, that would be equal to t. Okay, these are what are known as the symmetric equations. So we actually have three ways we can represent the equation of a line. We can do it with the vector equation, we can do it with the parametric equations that are shown right here, and we can do it with these symmetric equations. And you may be asked for one or both or all three depending on the problem. So just be careful, pay attention to what it's asking you for. Alright, usually once you have one, the other one is not too bad. Now I want to talk a little bit more about that vector equation, the form that you're going to be asked to put it in. So let me do that here. The vector equation of a line. I mean, we've established it, but I just want to kind of show you a little bit different way of thinking about it and the form that you're going to be asked to put those in when you're asked for a vector equation. So again, let's suppose I got some line running through R3, and let's suppose I have some point on there that I know is on my line. Call that x naught, y naught, z naught, and some other point here that I want to be on my line, x, y, z. Okay, what I'm going to do is I'm going to form the vector r, and as a position vector, it's just going to be the vector x, y, z. In other words, it's going to be the vector that starts at the origin and ends at the vector x, y, z. And I basically then want to describe how I can form that vector. Well, let me also form the vector r naught. That's going to be the vector that starts at the origin, ends at that point on my line, x naught, y naught, and z naught. Okay, and then of course I have my vector v, which is my, let's see if I find a color here I haven't used yet, which is my direction vector. Let's suppose that's v right here. So it's a vector that lies on my line. I'll give it the components a, b, and c. Okay, so the question again is, how do I form this vector r from the vectors r sub 0 right here and v right here? Well, you can see that if I take r sub 0 and add some scalar multiple of v, I get the vector r. And so r is going to be equal to r sub 0 plus some scalar multiple of my direction vector. In other words, r would be equal to the vector x naught, y naught, z naught plus t times a, b, c. Or, as you may be asked to enter it in this form, x naught I plus y naught j plus z naught k plus t times ai plus bj plus ck. Alright, let's go ahead then and start looking at some examples. Suppose I want to find the equations of the line that goes through 2 points. So just like in R2, 2 points determine a line here. We'll say the first point is P is 2, 3, negative 7, and the second point we'll call that Q. That lives at negative 7, 0, and 5. So we need two things. A point on the line, we have that. In fact, we have two of them. The other thing we need is a direction vector. So let's go ahead and find our direction vector. Any vector that lies on that line will work. I'm going to call it V, and I'll go ahead and take the vector that goes from P to Q. So the components of Q minus the components of P, that's negative 7 minus 2, or negative 9. 0 minus 3, that's a negative 3, and 5 minus a minus 7 is 5 plus 7, which I believe is 12. Now, again, any vector that lies in that line will work, so any scalar multiple of this will work as well. In fact, I'm going to make it a little bit easier to work with. And I'm going to cut everything here. Everything is a multiple of 3. So I'm going to use my direction vector to be negative 3, negative 1, and 4 instead of negative 9, negative 3, and 12. Doesn't matter. It still lies on our line. Okay, so here we have this line running through space. We've got this point P here, this point Q here. Originally I formed this vector V, but what did I just do? I said, actually I'm going to take that one, a third of that. Let's cut that back, and I'll take this vector here to be my vector V. Okay, now let's start with our vector equation. We'll do all three. Here's our vector equation. R, which is going to be the vector from the origin to get to any other point on my line, is going to be equal to, I'll take P as my point, but I'm going to form the vector from the origin to that point. So I'll say it's going to be equal to 2, 3, negative 7 as a vector, plus T times my direction vector of negative 3, negative 1, and 4. Or if you like, that's an R there, R is equal to 2I plus 3J minus 7K plus T times negative 3I minus J plus 4K. Okay, now let's turn our attention to, let's do parametric. Okay, so here we would think about this as, alright, that vector to go from P to any other point on my line. Say I got some point out here, x, y, z. I'm going to form the vector rather, from P to that point x, y, z. So it's going to be x minus, let's see, what was P here? It was 2, 3, negative 7. So the vector from P to any other point x, y, z in my line would look like x minus 2, y minus 3, z minus a minus 7, or z plus 7. And that vector could be formed by taking a scalar multiple of this direction vector v. That's equal to t times v, which we are using negative 3, negative 1, and 4. So equating components here, I have that x minus 2 equals negative 3t, y minus 3 equals negative t, and z plus 7 is equal to 4t. Solving for x, y, and z here, I have x equals 2 minus 3t, y equals 3 minus t, z equals negative 7 plus 4t. Those are the parametric equations. And finally then, let's do our symmetric equations. All we do here is from the parametric solve each for t. So I have x minus 2 over negative 3. That's equal to y minus 3 over negative 1, which is equal to z plus 7 over 4. Those are my symmetric equations. So any ordered triple x, y, and z that satisfies that series of equations is going to be a point on this line. Now again, if we look at these parametric equations, we call t our parameter here. And so you can find points on your line by just putting different values in for t. For example, if you put 0 in for t, you get x equals 2, y equals 3, z equals negative 7. You get this point right here. If you do t equals 1, you're just taking your point and adding on one copy of that vector. Here's the point where t equals 1. So here's the point where t equals 0 using my parametric equations. If you let t equal 3, what do we get? You get 2 plus 9, which, 2 minus 9, which is negative 7, 3 minus 3, which is 0, and negative 7 plus 12, which is 5. You get this point right here. This is where t equals 3, because that's your starting point plus 1, 2, 3 copies of v. And so you can see how you can get any point on your line that way by letting t be different things. Okay, now we have the concept of parallel lines in R2. Recall that in R2, lines were either parallel or they intersected, assuming they are distinct lines. Okay, so you have those two possibilities, pretty straightforward. Either you got a couple lines that run side by side forever, or if they aren't exactly the same slope, at some point they're going to intersect. Well, we actually have a third possibility here in R3. In R3, two distinct lines will be parallel. So we still have that. They could have the same direction vector or parallel direction vectors. But they could also intersect, of course. Or if you think about it, you could have two lines that aren't parallel and don't intersect. Take your fingers and put them at different angles and see how they could go by each other without intersecting at all. We call those types of lines skew. They can be skew lines. And we want to be able to determine if lines are parallel, intersecting, or skew. So let's do one example of that real quick. So let's suppose I want to determine if the following lines are just that, parallel, intersecting, or skew. And let's go ahead and let L1 be given by these parametric equations. X equals 1 plus 2t, y equals 3t, z equals 2 minus t. And L2 will be this. Parametric equations also, x equals negative 1 plus s. So I'm using s as my parameter here to avoid confusion. Y equals 4 plus s. Z is equal to 1 plus 3s. Now right off the bat, I can see what my direction vectors are. I'm going to call v1 the direction vector of my first line. That's the coefficients of my parameter, if you recall. That's 2, 3, negative 1. What about v2? The direction vector for my second line, the coefficients of that parameter, 1, 1, and 3. And so we can clearly see that these vectors are not scalar multiples of each other. So we can rule out the case that these two lines are parallel. They're not parallel because their direction vectors are not parallel. They're not scalar multiples of each other. So they're going to be either skew or intersecting. What we're going to do is assume they intersect and then try and find values for our parameters that would make that happen. So I'm going to try and find a value for t and a value for s so that the x, y, and z components are all the same for those values of s. Alright, so if they intersect, then the x terms would have to be equal. That is, 1 plus 2t would have to equal negative 1 plus s. The y terms would have to be equal for certain values of t and s. 3t would have to equal 4 plus s. And the z terms would have to be equal for certain values of t and s. 2 minus t would have to be equal to 1 plus 3s. So we have a system of equations here with two unknowns, and so you can just pick any of those two equations to try and solve for those two unknowns and see if it makes the third equation true as well. So it doesn't really matter which one here. I'll just go ahead and take the first two and try and solve those two equations for t and s. I'll get a solution here. The question is whether that solution will also make the third equation true. If it does, we have intersecting lines. If it does not, then we do not. So from this fact here, I can solve this one for s. And adding a 1 to both sides, I see that s is equal to 2 plus 2t. My daughter hates this problem. And then here I can solve this one for s. And I get that adding or subtracting 4 from both sides, I get s is equal to 3t minus 4. Okay, so I just pick two equations, solve them both for s. And so now I should be able to equate these two here. 2 plus 2t has to equal 3t minus 4. Solve this for t. Minus 4, so adding 4 is 6, subtracting t. I have that t is going to have to be equal to 6, and in that case, s is equal to 2 plus 2 times 6. That's 2 plus 12, or 14. So the question now then becomes, are the z-coordinates the same? These two z-coordinates here when s is 14 and t is 6. If they are, we have intersecting lines. And it'll be at that point when t is 6 in the first line where s is 14 in the second line. That'll give us the same x, y, and z coordinates. Well, for line 1, z is equal to, at this point, 2 minus 6, which is negative 4. For line 2, z is equal to 1 plus 3 times 14, which is 43. So these, in fact, are skew.